Hello everybody, my name is Sanae Tajali and I'm going to talk about laser powder bed fusion of new developed alloy, which is 316L alloy modified by copper, focusing on AI-assisted process parameter optimization, microstructure and mechanical properties analysis. Today, in my presentation, I'm going to start with a brief introduction on the topic. Then, materials that have been used in my research will be presented together with the methods of analysis. The results will be reported afterward following a deep discussion of them, and at the end, conclusions will be drawn. Additive manufacturing, as one of the most important pillars of Industry 4.0, enables us to produce complex shaped geometries in a layer-by-layer manner starting from a CAD file. This process for the metals can be classified into two main groups in the powder bed fusion and directed energy deposition. AM as a new technology has some advantages and disadvantages. In terms of advantages, it offers freedom of design and customization. On the other hand, as for some of the main limitations, the first limitation relates to poor surface quality, which often requires post-processing. Other main drawbacks including limited build size as well as low build-up rate, since the process constructs items in a micron by micron manner. But apart from these limitations, availability of the materials for this technology is a concern. So there are several ongoing research to overcome this limitation. One of the main solutions to overcome this issue is developing new materials. However, developing new materials can be costly and time-consuming. So it's essential to adopt new approaches to make the process parameter optimization more sustainable, fast, and reliable. This would enable us to optimize process parameters for various purposes like maximizing productivity, minimizing defect content, or achieving the best surface quality. So, as a main objective in this study, after material development, I used AI-assisted process parameter optimization approach through machine learning to make the relationship between process parameters and defect content in the newly developed alloy. Accordingly, in order to develop our new alloy following in situ alloying, first step is powder preparation. So 316L stainless steel powder mixed with 2.58% of copper in a jar mill without ball for 24 hours. And as you can see in the scanning electron microscope image, we have a good distribution of copper within the steel alloy, and then we can see round particles with some irregular shaped particles, including satellites around the big particles. What's more, after powder preparation, EDS elemental maps also showing the distribution of chemical elements within this specific alloy. After mixing, powder mixture was processed through laser powder bed fusion technology using Print Sharp 215 machine supplied by Prima Additive. In this process, powder mixture is placed in the powder container. Then by means of free coater, a thin layer of powder is spread all over the building platform, and finally laser selectively melts the layer according to the CAD file. Another step in developing new material is the design of an experiment. And in order to find the optimum process parameters, a wide range of them have been considered in this study. Laser power varied from 100 to 340 watts, a scanning speed from 400 to 1000 millimeter per second, and hatch distance from 0.1 to 0.2 millimeter. Ultimately, constant layer thickness of 13 microns was maintained for all the experiments. As-built samples after the LPBF process were characterized in terms of residual defects by three techniques of Archimedes method, image analysis, and X-ray computed tomography. And at the end of this research, microstructure and mechanical properties of some of the optimum samples have been analyzed. Archimedes method used as a rapid technique for analyzing the amount of porosities in all of the samples. However, to confirm its results, two additional methods of X-ray computed tomography and image analysis are also applied on some of the random samples. And due to the perfect alignment between these results, Archimedes method was validated as the main method for analyzing amount of porosities in this analysis. The relative density of all of the samples here is plotted against volumetric energy density, which reflects the combined effect of different process parameters as energy input per unit volume. As shown in the figure, insufficient energy density results in lack of fusion defects, while excessively high energy densities can cause gas-induced porosities, both of which reduce relative density in this alloy. Finally, to better correlate process parameters with final relative density, an AI-assisted method through machine learning models was applied. And this approach involved hyperparameter tuning and selecting the most accurate model to predict relative densities, which was support vector regression in this study. After selecting most accurate model, when we are going to select the combination of different optimized process parameters by means of this model, I mean support vector regression, for different purposes like productivity, dimensional accuracy, or surface quality, we can also predict amount of defect inside our samples. Up until now, the machine learning approach is completed, and then in order to link the process parameters and microstructure, we characterize different samples at different volumetric energy densities. And as you can clearly see in these pictures, by increasing volumetric energy density that we have high energy input, we can expect larger melt pools based on the thermophysical properties of this specific alloy. The microstructure analysis confirms the distribution of copper in the as-built microstructure is rather homogeneous and no segregation, no peak was revealed due to the formation of extra phases related to copper. And we can also notice a slight differences in the microstructure after adding copper, such as formation of some irregular grains. In the final part of this study, we compared mechanical properties of this alloy with and without added copper. We found that adding copper can slightly improve both the mechanical strength and toughness of the material. And analyzing the fracture surfaces of these two alloys showed a more ductile fracture pattern with smaller dimples in the copper-containing alloy. Finally, the main conclusions of my research are listed here. Support vector regression was the best model for predicting LPBF process parameter defect content relationship. Higher energy densities create deeper melt pools, while lower energy densities produce shallower melt pools. According to the X-ray diffraction analysis, the copper atom dissolves into the iron and forming a complete austenitic structure under the LPBF process. And tensile test results show that even a small copper addition can have a slight impact in the mechanical properties of as-built 316L alloy. Regarding my research outcomes, the results of my work have already been published at different journals. The review paper based on the application of machine learning in laser-based metal additive manufacturing, published at the International Journal of Advanced Manufacturing Technology. Then two additional conference papers were published at the Second International Electronic Conference on Metals. Moreover, a practical paper based on enhancing additive manufacturing quality and productivity submitted to the Progress in Additive Manufacturing journal, and finally comparative analysis of density measurement techniques is under the phase of preparation, which will be submitted soon. Thanks a lot for your attention and consideration.